Okay, so now we want to talk about lower bounds on hypergraph Ramsey number. One natural thing is again to consider the arguments for graph Ramsey number and then whether it extends. And for graph Ramsey number, what did we do? We took a random coloring. And then we show that if you set up the parameter correctly, then you can show that your random coloring has positive probability that it doesn't contain any monochromatic KK. You just mimic that, then you get the following proposition. For any T and R at least 2, and then K at least T and R, the R color Ramsey number so R of them is bigger than R to the, say, K to the T minus 1 over T to the T. So this is exponent. And proof is, as I mentioned, you just take it as this number, like R to the K to the T minus 1 divided by T to the T. And consider random R edge coloring of T uniform n vertex complete hypergraph, which is chosen uniformly random. In other words, for each hyperedge, you flip a coin. Not coin. For each hyperedge, you choose one of the R colors independently for each edge, and then that gives you the highlight. And for vertex of K, vertex set of K vertices, the probability that it is monochromatic is again like R to the 1 minus K choose T. And you take the union bound, then what's the probability? That the probability is the no monochromatic KK at all is what? 1 minus N choose K, R to the 1 minus K choose T. And with our choice, you can actually show that this is positive. So that proves the existence of highlighting that avoids all monochromatic KK, T uniform KK. Okay, then what do you get? Just get the lower bound that the T uniform KK is at least what? 2 to the K to the some constant times K to the T minus 1. Okay, but what was the upper bound? Upper bound was like you take the stepping down argument, then this was the height, the tower function of the height T. There are considerable gap between them. For graph case, okay, so this is single exponential and this is also single exponential. So we have quite satisfying answers. But for higher uniformity, this is not so satisfying. Okay, can you get a better lower bound? And there is a lemma called the stepping up lemma. This is proved by Ergish, Einar, and Lado. Again, you can kind of see that stepping down was that you have a coloring on the higher uniformity graph, and then you step down, you derive a coloring for lower uniformity, and then you apply your inductive statement there to get the upper bound on the lambda number. Here it's the other way. You step down. You assume that you have stepping up. You have assume that you have a lower bound example for your lower uniform graph, and then you use it to construct a lower bound construction, lower bound coloring for your high uniform graph. That provides a lower bound. So again, but one catch is that here you have to assume that your uniformity is LS3. It doesn't apply for two uniform graph case. Then what? So for higher uniformity, let's say 2k plus t minus 4 and 2k plus t minus 4, this has lower bound, which is exponential of one lower uniformity. Again, this is R color, this is R color. If you know this, then what do you know? Because this is only for TLS3, it doesn't give any better bound for 3 uniform case. 3 uniform case, we have this gap. But the 4 uniform case, what can we get is this is 2 to the 2 to the 2 to the ck. And originally this was 2 to the k square, like k cube, but instead of that, you can use this stepping up lemma. So we have this lower bound. That means what? This is a lift like when t is 3. This is like 2 to the R3, like 3 over 2, essentially. Yeah. Just wait 2 columns. And that's what? From here, that's 2 to the C K square. So it improved. So this is tower type of height 4 and tower type of height 3. In the same way, you can take 2 to the ck. This is t, 2 to the ck square. The length is t minus 1. So this is much better than the situation before. So this stepping up lemma improves the bound, lower bound for uniformity LS4. So let's see how we can prove this. Again, we only prove for t equals 3 and r equal 2. 2 color case and then 3 uniform case. So what we want to show is that for 4 uniform case, 2k minus 1, 2k minus 1 is at least 2 to the 3 uniform lambda number minus 1s. So let's say capital N is the Length number of R33 minus 1, and small n is 2 to the n. Now what? What we want to do is, for this n, there is from this definition, we can take 2H coloring I of the complete 3-uniform hypergraph on n versus this on the vertex set bracket n, so number between 1 and n, that has no monochromatic KK in there. So because this is one lower than the Ramsey number, such a coloring must be easy. And now what? We want to consider a all uniform hypergraph on small n vertices. And what's the vertex set? For the vertex set of that all uniform hypergraph, we consider the tuples. So tuples B1 to Bn in 0, 1 to the capital A. So there are exactly n tuples, exactly 2 to the capital N, which is small n tuples here, which are ordered lexicographically. So 0, 0, 0 is first, and then 0, 0, 0, 1 is the second, 0, 0, 1, 0 is later, and then 0, 0, 0, 1, 1. And last one is 1, 1, 1, 1. So you give an ordering. So this is B1, this is B2, B3, and so on, Bn. So we write Vik with the case coordinate of this Vi. Then we define the following function. So for any pair, Vi and Pj, we let delta of Vi and Pj be the minimum k such that they differ. So you see these two differ at the last moment, nth coordinate, capital N, and this delta value is capital N. On the other hand, this and this differs at the first place, so delta value is 1. This and this, the first time it differs is the n minus 1th place. So capital N minus 1 is this delta value. So this definition is clear. Then for any set 4 vertices, say BA, BB, BC, BD, with A, B, C, D in its order, what we do is we define our pi prime, which is our desired coloring, our coloring of the 4 uniform graph as follows. What do we do? We first compute delta 1, which is delta of BA, BB, and delta 2, which is delta of BB, BC, and delta 3, which is delta of BC, BD. And then we keep the color based on the patterns of this delta. So if this is monotone, so either monotone increasing or monotone decreasing, then you keep the colors of these 3 uniform you see your 3 uniform hypergraph. And then delta 1, delta 2, delta 3 is between 1 and capital N. So that's already colored by your type. And then you see that, and then you use that color. And if like this is like concave, so the V2 is the maximum, and we color it red. And if V2 is the minimum, so it's like convex, then you give it blue. Then we will claim that this is the good coloring for our 4 uniform hypergraph. Okay. Why? Before verifying it, let me collect some property of this delta. So one is that if you have Bi, Bj, Bl, say I, J, L in this order, and Bi, Bj is never same with delta Bj, Bl. Why? If this is K, then what? You have Bi and Bj. If it's 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1. And then B is like 0, 0, 0, 1, 0, 0, 1, 1, 1, something. But this is case coordinate where they differ first. And BL is the later one. But it's not possible that you have again, everything same and this time it's different. If you want to differ it, this is bigger and then L is bigger, means that you have to increase, but there is no room for increasing. You cannot write 2 here. In order for this to be bigger, I mean, something has to be higher here. So this is not possible. So these two are actually different. And also, you can verify that the Bi, Bl, delta Bi, Bl is actually the minimum of delta Bi, Bj, and delta Bj, Bl. Why? I mean, this differs at K, and then this differs at L. That means all the previous ones are actually the same. So first time, so let's say these two differs here. So this is the first time they differ, then everything here is same. And then these two are also same. So this is the difference. So first time the first one and third one differs are this coordinate. So that shows this. More generally, if you have I1, I2, IS, then delta BI1 and BIS is minimum of delta BI1, BI2, delta BI2, delta BI3, and so on. Delta, you just take the delta on all consecutive one and take the minimum, let's say. Okay, so now we show that with respect to this pi, we have no monochromatic clique. So assume that BA1, BA2, BA, say 2K minus 1 from so we 2K minus 1 because this is what we want to show. This coloring we show that this doesn't contain clique of size 2K minus 1. So if this forms a red monochromatic clique in coloring pi prime, I mean, it could be red or blue, but without loss of generality. Let's say it's red. In the blue case, the argument is saying. Then let delta I be the delta of b a sub I and b a sub I plus 1 for each I between 1 and 2k minus 2. Then what? What do we know? From the definition, this is a red monochromatic clique, means that it's pi prime or BAI, BAJ, BAL is never blue. But how do we define this blue? If this is convex, then that's blue. So this never happened. So AI minus 1. So, I mean, just consider the 3 consecutive one. AI minus 1, AI, AI plus 1. AI. This never happened. So, that's the sequence delta 1 to delta 2k minus 2. And sorry, according to our definition for this delta here, does not have I. So this doesn't happen. So what does it mean? If it increase, and then at some point it start to decrease, that's fine. But it decrease and at some point it start to increase, then that's problem. So this pattern doesn't come here. So only possibility is that this one is unimodal, meaning that it increase and at some point it can decrease, but that's it. Meaning that say there is this S such that delta 1, delta 2, it increases up to S. And then it starts to decrease. Okay. And now what? Now, from here, you can see this red and blue plays a role that essentially this give you a long monotone sequence. You have a sequence of length 2k minus 2. And let go blue means that it increase and decrease. If it is lack of red, so if it is blue monochromatic, then it should decrease and then increase. No other pattern. That gives you long monotone part, either long increasing part or long decreasing part. But due to our choice, that just, I mean, that's same as like how you get from the same pattern from the 3 uniform coloring. If say S is at least K, then you have delta 1, delta 2, delta K is strictly increasing. Then what? By the definition of pi prime, which uses the same color pattern with pi when it is monotone. So the set delta 1 to delta K, they must form a, because I mean you choose that this forms a red monochromatic clique. And that means that this was red. So that forms a monochromatic red KK, 3 uniform KK under the coloring high, a contradiction. And if S is more than K, then what? You take delta S plus 1, to delta 2K minus 2. And then this is also monotone strictly decreasing. So same argument apply. So this proves that this stepping up actually works. So, as I mentioned, this provides the bound this is power of I t minus 1 and t, one difference. One big open problem is to closing this gap. The conjecture is that it is actually the tower of height t. In order to prove this, all you have to do is proving for 3 uniform cases. Again, the difference comes from the fact that we don't have a good lower bound for 3 uniform case except this one. So this is the best one. If you upgrade this to height of, tower of I3, then it will solve the conjecture. And there is some reason why people believe that the upper bound might be close to the truth. Why it would be tower type of height t instead of t minus 1. Because there is an argument found by Heiner, which is similar to the stepping up lemma. We prove that there is a way to make changes on this argument so that it also works for t equal 2 case. Here, you can kind of see that this kind of pattern doesn't arise if there are only 2 of this. If you have at least 3 of this, okay, you have like this kind of thing. But when you have only delta 1 and delta 2, it's either increasing or decreasing. It's difficult. Right? So this argument only works when you start from like uniformity 3. You cannot start from uniformity 2. But Heiner found a way to make it so that it starts from uniformity 2, but it requires more color. There are two eye color. Then you start from uniformity 2 Ramsey color with eye color. So he found the modification of the stepping up lemma that this works. If number of colors is more, then what does this provide? It provides that if you have at least 4 colors, 4 or more, then you have the correct bounds. So this is T. This is also T. So this is circumstantial evidence that maybe 2 colors or 3 colors, the similar thing is true. Okay, so that was about the Ramsey number of hypergraph that we have learned. Okay, thank you for listening. Yeah, next time we will start a new topic.